Good morning everyone. We're going to speak about airline demands and challenges we face as performance vendors. So at DynamicSource, among other things, we work with IATA on performance applications, and we get a lot of input from airlines, and I'm going to present a few of them, how we meet those challenges, and also some issues that are still there. So the agenda for today will be first to discuss the fundamentals. We're going to look at an overview of the airline demands. I'm going to tell you a little bit about the vendor solutions we have. Then we're going to focus on some of the issues which we still haven't been able to solve. And also how we could use machine learning to help us out. So, said that, we're going to go to the fundamentals then. So, for takeoff and landing performance, the goal is to either stay on the runway or make it back safely in case of an unexpected event. And to do these calculations, you have hundreds of input variables. Atmospheric conditions, aircraft configurations, runway data, and also data from the surrounding around the airport, obstacles and such. And to do these calculations, we have the SCAP, which stands for Standardized Computerized Aircraft Performance. What it basically is the airplane flight manual together with aircraft proprietary data bundled together into a calculation engine. And these engines can take two forms. Either it operates under second principles, which is basically table reading. So the computer just reads a table just like you do in the AFM. It's very fast, but the bad thing is that you have to use a lot of let's say, it's not optimized. You have to have a few boundaries to allow someone to read something from a table. Whereas first principle calculations is using natural law. So you can get very optimized performance that way. You can get a few tons extra takeoff weight that way, or reduce the thrust for takeoff a bit more and then save maintenance and fuel. So first principles is the way to go, and pretty much every OEM is there right now. The bad thing, if we want to say something bad about first principles, is that the calculations are very complex, so it takes time. So I'll get back to that a bit later. And as I mentioned, the SCAP is a standard, and IATA has a task force consisting of OEMs, airlines, and vendors. So everyone works together to create a standard. So, if we're going to look at the airline demands, I'll give you an overview slide. We have cross-platform compatibility, so we need to be able to run the performance software on Apple devices, Windows devices, Android, Linux, whatever. And that is met. As performance vendors, we need to tailor the graphical user interfaces depending on airline requests, use the airline's proprietary algorithms. They might have a flat request that differs a bit from the OEM. You have to have a lot of management tools to import airport and obstacle databases and user management and stuff. And these management tools may consist of much more code than the actual performance application itself. So I'm not going to discuss that more now, but that's a huge part of the overall solution. Then you also need to provide testing tools. So let's say CAA audits, when you update the application, you need to be able to test it, and you need to be able to look at the performance calculations in a very transparent way, because they are operationally critical, so they just can't be wrong. And with the EFBs and the powerful computers today, we store we generate a lot of data. We need to have tools to also extract that data. We can use data mining and other statistics on that data, so to say. And then we have two issues which no one in this room or anyone in this industry has been managing to solve. And that is what John just brought up with the diverse fleet support. Then we also have an issue with the EFB programs getting bigger. When you get more and more applications, you want to have a unified user experience, and we have a big issue there. And then I'm gonna just touch upon a safety thing regarding sanity checking the data you trust. So let's head on down to the vendor solutions. So this is a very messy slide, but for the system, the performance systems you build, you want to use the best tools for each and every part of the system. And that ends up being heaps of programming languages, databases, and so on and so forth. This is just a fraction of everything you need to work with. So how do you sort out this mess? Well, over the years, here, get to the next slide. Stop. All right, you can see. Here we go. Yeah. So if we take all of these software and databases and we categorize them in 2 categories, we have the closed source software and databases, and we also have the open source ones. And over the years, we've sort of drawn the conclusion that we get much better results using open source software. And some of the advantages is that you have transparency, because everyone has the open source available to them. You can dig into the code and so on and so forth. You're much more likely to have open source adapting to standards. It's auditable, given the transparency I just mentioned, because it's a huge developer community that gets access to all of these programs. You have the best developers helping you. And given the transparency, it also provides security, because all bugs are shadowed with enough eyeballs looking at them. And it provides you with freedom. Just as the previous speaker mentioned, you can modify open source software to make it work as you'd like. And then you contribute to the whole project by putting those changes back into the software. And with a huge developer community, every problem you have, someone already had before, so you get very good support, and it's less costly. But still, even though it's open source, it's still 18 different programming languages and so on and so forth. So by using package control systems in an operating system called Linux, which is also open source by the way, you can bundle all of these systems together in just one package. So it behaves as one development tool for you. And that opens up a lot of possibilities. So I just want to reiterate a quote I just said. So one of the founders of Linux, he says that given enough eyeballs, all bugs are shadowed. And we've seen that over the years with open source software. And it was a long session yesterday about security and data integrity, so I'm not going to go too deep into that. But let's say you have your trusted environment. And in that trusted environment, you have your 3 systems. And you want to communicate with other vendors providing data to your systems. That can be airport and hospital database vendors, for example, when we relate to performance. So even if you trust vendor A and B, it's still very wise to sanity check the data they provide, because there might be missing runway parameters, let's say excessive distances, and so on and so forth. So even though you trust that vendor, you shouldn't trust the data, because it's easy for everyone to make small errors. And performance is such operationally critical that you should sanitize the data before you use it. And I also want to mention the single source of truth, because in the connected environment we have today, you might have an offline EFB on your aircraft providing you performance calculations. You can also get the performance calculations sent to the aircraft via, for example, ACARS. And how do you know then that the calculation engine on your iPad is the same as the one that gives you the numbers via ACARS? So as a performance vendor, you should build a calculation engine, the wrapper around it, and all systems integrating with it, so it's platform compatible, cross-platform compatible. So you can put it on servers on the ground and also on the offline EFBs. That's very important. So I'm going to go back to the issues we face then. So In the beginning of an EFB program, maybe you have 3 apps. You have maps, performance, and manuals. And it's easy enough to just tap each of one of those apps, update them, and so on and so forth. But as the years go, you get more and more EFB applications. It's a mess to keep everything updated and up to date, so to say. So what everyone is looking for is to get either all apps into one app, or make them behave like they're in one system. So basically a unified user experience. You want single sign-on, so you don't have different login and passwords for every app. And one update button that updates all the 50 EFB apps you have. You can share the data in between them, and so on and so forth. So there are 2 ways in the aviation industry right now to accommodate that. You can either use the locked environment, or you can use the open environment. And the locked environment basically means that you program all your apps together into one app. And it might be an OEM that supplies you with performance, manuals, and charge. And if you want to add a new app to your EFB program, you need to ask the OEM if they would allow that vendor to program their app to fit within their locked environment. And then, if you want to add apps, they need to recompile their app. And let's say that you have one of these locked environments from one OEM, and you have a performance application that runs multiple aircraft types, and another OEM updates their SCAP. That's a critical update, and you need to do it fast. But as there's another OEM controlling this environment, you might not be able to do it as hasty as you need to. So it gives us a lot of problems with these locked environments that are everywhere here right now. And the alternative, of course, is an open environment. So here it says central command. That could be an app which the airline creates themselves, or a vendor. And then you should just be able to plug and play, so to say. Add charts, add manuals, just pick and choose the best vendors you'd like and make them work like one unified system. The problem here is that without standards, an open environment easily turns into a locked environment, because you're going to have rules of plug and play these apps, so to say. So you can't really connect everyone. And that's why I want to refer to Sonja's presentation yesterday regarding the A840, which is now being upgraded to accommodate an open environment and set an airing standard for it. So if you think you can contribute, please contact her, so we can get somewhere with this. And I also want to say that the locked environment is very likely not to have any standards at all. You know what that means? It locks out developers, and it's not an even playing field anymore. And now we're going to go to something more fun. We're going to speak about machine learning. So as you run these first principle calculations more and more, which I described in the beginning, we feel the need for speed. So let's say you have a flight planning system that is going to calculate a departure airport, arrival airport, a few alternatives. And on each and every one of these airports, you have multiple runways, intersections, and you want to optimize these calculations to get the best flight plan. Save as much money as you can. So when the dispatcher presses calculate, it might end up being 60 calculations being sent. And then you have 60 first principle calculations that needs to be done. And if that queues up, you might end up having to do 5 hours of calculations during one peak hour. And that doesn't really work. So how do you reduce the calculation time? Well, the most obvious way to do it is to use parallel computing. So you have a performance API, which a flight planning system speaks to. And that performance API just shares the load with multiple servers. So that's the most obvious way. And a very easy way of doing this is to use the cloud. Because you have data centers all over the world, it's easy to scale up, and you have the redundancy. One center goes down, another one takes its place, and so on and so forth. And also if you fly globally, you can always have a data center close to your operation, and that is also very beneficial. But then there's another way, and that is, what if you don't have to send these requests to the servers? So I'm going to introduce to you let's see if it shows up, the performance robot, which uses machine learning. So what is a performance robot? Basically, we're going to speak about its brain, but just to visualize it a little bit better, I'm going to have a robot here. So the age of artificial intelligence is here, but in fact, artificial intelligence has been here since the 50s. Why do we speak about it so much today? Well, 90% of all the world's data has been generated over the last 2 years. So we have a great need to dig into that. And using a machine is a great tool for that. So machine learning, that's a machine that is supposed to learn without any human interaction. That's artificial intelligence. And we can see these trends with generating heaps amounts of data within the aviation industry. So we need to fight and accommodate that as well. So the performance robot, what it will do is predict questions. So let's say you have flight crew and you have dispatchers sending heaps and heaps of calculations to the servers. If you have a robot in between that already knows the questions, the robot already knows the answer, and it will just bounce back without having to take any server capacity from them and so on. And it's very fast. So how do you accomplish that, and how do you trust it? So the key to trusting a performance robot is to understand that the performance robot will predict questions, not answers. So the performance robot will not guess what the V1 will be. It'll just 2 hours before, let's say, a departure in Chicago, it'll guess what will the dispatchers and what will the pilots ask for. And if the robot has already asked the same questions as they will do 2 hours later, it already knows the answer. We're not guessing answers, we're guessing questions. And how do we train the robot to do that? I'm going to show you first a diagram of it and then a visualization of it. So first, we have to establish a goal. So for this sake, we're going to say that we want to predict the temperature in Chicago of February morning, because we have a peak hour and we have a lot of flights departing. So the goal will be to predict what temperature it will be in 2 hours. And then we're going to establish a behavior with that robot. And that robot's behavior will start randomly, just guessing temperatures, maybe based upon a TAF to get a little bit closer. And at this moment, the programmer takes its hands off the system, so the machine will do the rest now. So what happens next is that it spawns thousands of these performance robots to create a population of robots. Everyone is just randomly guessing temperatures. And after they've done that for a while, you look at how many of these 1,000 robots have reached the goal of guessing the temperature it ended up being 2 hours later. And if it's just a small fraction of these robots doing the right guesses, you take these robots and then you evolve them. So basically you make the robots and then you create a new generation. And then this circle continues until enough robots in this population of 1,000 robots are able to predict the temperature. So it just goes around and around and around. And it's very difficult to get all of the thousands of robots to guess the temperature right. But maybe you'll have 900 of them correct. And then you say, yeah, I reached my goal. And then you have a performance robot able to guess temperatures of February morning in Chicago. But that's all it can do. But given the powerful computers we have today, and this massive computing we get with the cloud, you could easily have a robot to predict all these 100 input variables a performance calculation consists of. And it's very likely that if a robot wakes up a few hours before let's say an intense departure time at an airport, a lot of the calculations which the pilots and the dispatchers are doing have already been solved by the robot. And that reduces calculation time significantly. So, this algorithm I just showed you is called the genetic algorithm. And what we have here is a simple creature called the random one. It's the first generation of this creature. It has 3 limbs. And we first start by establishing a goal. That's what the humans does. We say that it should avoid the ball on the right-hand side of the screen coming at the robot or the creature. And the behavior of the creature will be just to flip its limbs around a little bit, and it's also able to stretch its limbs a little bit. And we'll see how that goes. So the ball starts to roll, and it just randomly flips its limbs around. And what you see here is just one creature out of that population of thousands of creatures. And let's say that maybe 50 of these creatures were quite successful in lifting its limbs, so it didn't touch the ball a lot, so to say. Then you take these creatures and you involve a new generation. And if we fast forward here to generation 4, we can see that this one had started to notice it has arms and lifts them up. Then you take the best performers of this generation, and now we end up with generation 10, which is the teenager. It's just sitting there, not really giving a shit. But at least it learned by having the hands up like this. It avoided the ball quite successfully. So that's something that will continue to evolve in this creature, so to say. So then by generation 38, the creature has now learned how to stand up. So we fast forward that, and now we have the jumper. So in generation 71, a few of them in that population has learned how to jump. So we take all the jumpers, and then we fast forward a little bit, and we end up with a candidate that successfully jumps over the ball. So remember now, from generation 0 up until here, there has been no human interaction. The computer has just worked out this itself. And if we now, as humans, establish as a new goal, which could be moved to the right, well, by generation 211 of that, it's learned how to walk. Well, of course, we don't want performance robots to walk away, but this is how dynamic it is, and it's a very dynamic, let's say, world we live in, so it needs to be able to adapt all the time. So, the way to reduce the calculation time of this 1 minute of calculations that the dispatcher sends is to use parallel computing and machine learning. And this is a graph taken from the reality by combining that. But it's still not good enough, but we have robots working on it, so hopefully soon it'll get better. And the conclusion with this presentation is that there's brilliant developer communities in the aviation industry. The problem is that they are fighting with their hands behind their backs. So the only demands set by airlines that are not met is where monopolistic practices prevails. And we all know the reason for any game of Monopoly is it's not likely that somebody will win. It's not likely that everyone gives up. It's most likely that someone flips the board over in rage. And the ones that flips the board over, that's the airlines. So we want to say that healthy competition leads to high quality products, cost efficient solutions. It promotes innovation, most importantly. And all airlines benefit from this. And adapting to standards, then you also give new developers the chance to come into this industry. Because, I mean, the aviation industry, we fly planes. We should lead the way. So instead of, having these silly fights, unfair fights, just let all the developers fight on the same terms, and we will lead the way, finally. So thank you so much for this.